Hello, it's John again, and I am here with a bit of information for our standard N2, trying to think about prime and composite numbers and factoring. This is one of my favorite things that comes up in elementary school because it proves that the math that elementary students are doing is deep and it's important. So this math that we're talking about today goes back thousands of years. It's one of the one of the earliest important theorems for which we know there was a proof done in the ancient world. It's recorded in Euclid, and we don't know. We usually think about Euclid with geometry, but he also had quite a bit about number, and this is connected to what's almost the first theorem in his books. Um, Okay, but it all comes back to factoring, to this idea that we're trying to learn how to think multiplicatively instead of just additively. Thinking additively is important. It's related to a lot of phenomena, but anytime we have something happening that's proportional to how much is there, it's going to be a multiplicative situation. And so giving kids a foundation under which they can build onto which they can build their multiplicative understanding for future courses is pretty important. All right. What we're going to start with are these factoring. So one of the traditional diagrams is called a tree diagram to do factoring. And you take a number like 24 and you write the factors, how it factors. And then, so 4 times 6 is 24. But we could factor 4 again into 2 times 2. And we could factor 6 into 2 times 3. Now, are any of those numbers a multiple of something else? I don't think so, right? 2, 2, 2, and 3. There's no further way to break those down. Well, you might say, well, we could say 3 is 1 times 3. But since we could do that with every number, and then we could do 1 as 1 times 1, mathematicians leave out 1. We don't talk about it as prime, and it's not composite. It's just something different. When we talk about 1 in this context of multiplication, we call it an identity, which means that when you multiply it times a number, you get the same thing back. So we're going to get rid of those. But what if we had started with a different multiplication to get 24, right? There's so many different ways to get 24. 2 and 12, 1 and 24. Well, we already said we're not using that one. But 3 and 8, that seems very different. Well, but then 8 we could break down into 2 and 4. And then 4, that breaks down into 2 and 2. So both ways we did it, we wound up with 2 times 2 times 2 times 3. And this big theorem I was talking about says that kind of no matter how we think about breaking it down, there's only one prime factorization. And that idea is so important, we call it a fundamental theorem. So a theorem is something that's been proven. It's not just a conjecture or a proposal. And there's 3 main fundamental theorems in mathematics. There's the fundamental theorem of arithmetic, which is this idea. There's the fundamental theorem of algebra, which talks about how many roots for polynomials. And there's a fundamental theorem of calculus, which talks about how derivatives and integrals are related to each other. So this is a big freaking deal. And it's something that 4th and 5th graders can start to build their understanding of. So the prime factorization, we can rearrange them, but any way we factor 24, it would turn into 3 2's multiplied together and 1 3. All right. So what we're going to do with this idea of prime factorization is a math and art project. And I love combining math and art. I love both things individually, but putting them together has been really powerful in my experience. It allows students access, and you know how much I care about that, this idea of low floor tasks. But it has a double benefit in that people who don't think they can do art, for some reason, it makes them feel like maybe this is something they could do as well. So even though art and math are the two subjects that maybe suffer the most from fixed mindset, um, combining them seems to create more access. And it helps make math more playful, which, as we've talked about all semester, is something that is important and rare, right? That math is something that where we're being creative. All right. So the idea of this is to find a number that's a good number that breaks down in a lot of different ways. And I started out doing this thinking about maybe a number that's important. So 1964, that's when I was born. I am so freaking old, you guys. So I tried to factor that out, and it factored into 4 times 491. And even though 491 is big, it's prime. There's no way to break it down. It's not a multiple of anything. I'll teach you one of my favorite tricks to check for if it's a multiple of 3. You add up the digits. 4 plus 9, that's 13, plus 1, that's 14. If it's divisible by 3, the sum of the digits will add up to a number that's divisible by 3. And the same thing's true for 9. Other numbers you have to just check. We can tell right away it's not a multiple of 5. If you try dividing in 7, well, 7 times 70 is 490, so I won't go into that. You could try 11, but 11 goes into 440. That would leave 51 over, and 11 doesn't go into that. And so whatever other numbers we try, there's not going to be something to go into it. And this is a pretty boring tree. So I thought about doing 1997. That's the year I got married. I was an old guy getting married. But it turns out that that number is prime. I actually kind of like that because prime numbers are cool to mathematicians. And so I thought, what about the year my first kid was born? That number is prime. How could we know those things? Right? So a tool that we haven't used in class is Wolfram Alpha. So it's just wolframalpha.com, and it's free, and it's not exactly a calculator. It's what Stephen Wolfram calls a computation engine. So you can ask it all kinds of mathy questions, and it'll give you the answer. The existence of tools like this is a lot like a lot of the reason why we want to focus more on reasoning. So you can see if I put in factor 1964, 1964, I get it's 2 times 2, 4 times the 491. It doesn't break down any further than that. So if I hit enter, you'll see it computing. And it gives you that. 3 prime factors, 2 distinct, which means there's a 2 and a 491 in it. All right. So instead, what I decided to do to build up my factor tree was to build a number. So I multiplied a bunch of factors together to get this number 21,600. Okay, so that's a pretty big number, but I liked the way it broke down. And what we're going to do is try to build a tree out of it. So, well, one way we could break it down, we could see right away that that's 100 times something. So 100 times 216, 100 we can factor 10 times 10, and both of those factor into 2 and 5. 216, let's see. Well, it's an even number. I could do 2 times something. 4 goes into 216, so I could break it up 4 times something even. So why don't I do that? So 4 times 50 would be 200. So 4 times 54 is 216. 54 is 6 times 9. And then 2 times 3 and 3 times 3. So I had an art teacher friend, Heather Minnebo, and she got interested in these factor trees and was trying to think of a project where we could kind of combine the math with the art. And she came up with the idea of actually making them trees. So we've got our 2,000, I keep saying that, 21,600 tree, and it breaks up into 2 branches. We did 100 times 216. We broke this one up into kind of a big branch and a small branch of 4. Well, I don't think I ever finished breaking that up on the other page, which breaks up into 2 and 2. That was 4 times 54. 6 times 9. 3 times 3. So when we were talking about this project, I talked about the fundamental theorem of arithmetic, how cool it was that no matter how we broke it down, we'd wind up with the same prime factorization at the end. And that gave her the idea. She thought that, well, maybe we could make a real tree with roots, and the kids could work on drawing stuff that was above ground and beneath ground, right? So we could think about how does this factor out in a different way. Well, 100 goes into it, but this number 216 was even. So that means 200 goes into it, which would give us half of the 216. I could break that up into 20 times 10, which does 2 times 5. This one we get 5 times 4, which breaks up into another 2 times 2. And 108, it turns out that's one of my favorite numbers. It breaks down in so many different interesting ways. It comes up in lots of ancient cultures as an important number. So 1 plus 0 plus 8 is 9. That means 9 goes into it. See, 9 times 10 would be 90. You need 18 more, so it must be 12. And then 9 factors into 3 and 3. 12 factors into 3 and 4. And then the 4 factors into 2 and 2. Okay, what other kinds of things live underground? Maybe I could draw a little cute mole. That's a mole. Maybe I could draw worms. Maybe there could be even a little rabbit den underneath there. Okay, so what you're going to do is you're going to make a picture of your own factor tree. I've, in the distance learning document, I've put the requirements. I want you to get a number that's pretty big, bigger than the numbers that we've been dealing with this semester so far. And then once you've got it, I want you to turn it into an art project, right? So we could make leaves at the end of this. Maybe I could even have it, it's spring, so it could be blooming, have some flowers. Maybe I want a number even bigger than this one so I could get kind of more branches and make it look more leafy, more tree-like. But that's the idea. Then we're going to post them to a common place to share so you can see everybody's, as well as the usual send it to me for evaluation and feedback. If there's any questions, of course, I'm available. Heather Anderson's available. Reach out and get it. And again, right, we're looking for growth mindset. So the math, I'm confident that you can do. The art, maybe it makes you nervous, but give it a go. See what you can make. Decorating in color, I'll work on a finished version of this and I'll post mine to the Flipgrid too. Maybe I want a bigger number though. I'll have to think about that. Hope you're well and be talking to you at least one more time. Thanks very much.